everyone, welcome back. My name is Mr. Cobalt, and in this video we're going to calculate the rate constant and half-life for a certain reaction when we're given the percent completion and the time it takes to reach that completion. Let's get into this. Okay, so in this problem we're told a certain first order reaction is 45% complete in 65 seconds. What are the values of the rate constant and the half-life for this process? So the first thing we want to do is we want to find out what the K value is, what the rate constant is. And they gave us that the reaction is 45% complete. First thing we need to do is figure out what integrated rate law we need to use, and that's going to be for the first order reaction. So we need to make sure we're using the right equation. So for the first order reaction, the integrated rate law is going to be the natural log of the concentration of some substance A at time t is equal to negative K times the time t plus the natural log of the initial concentration of substance A. Okay, so this is one version of the equation. The other version that you could use is the natural log of the concentration of A at time t divided by the concentration of A initially, and then that's going to be equal to negative K times T. Either one of these versions you can use. I'm going to go ahead and use this version, but you can use this version as well. It should get you the same answer. Okay, so now what about the concentrations? We don't have a concentration. All we know is that 45.0% of the reaction is complete. So whatever concentration we started with, we know that 45.0% of that concentration has been reacted and is gone. So 45% of whatever that initial concentration is gone, and we have 55% of that original concentration left. So we can use whatever initial concentration we want because we know that 45% of whatever that concentration is has been reacted. So we can choose the simple number of 1.0 molar. So if we choose that, we could say that the initial concentration of A is 1.0 molar. And then 45% of that reacts, leaving 55%, and 55% of 1 is 0.55 molar. So we can have A, the concentration of A at time t is going to be equal to 0.55 molar. And again, because 55% of 1 is 0.55, we could calculate that. So if you remember that percentage is equal to the part over the whole multiplied by 100. Well, what's the whole in this case? The whole is the initial concentration we started with. That's reacting, right? We start with a certain amount, it reacts, and it starts to disappear and go away while the reaction is going. So whatever we start with in the beginning is our whole. So that's the initial concentration. The part is what's left over after the reaction has gone on, right? So after a certain amount of time, we're left with a certain amount left over. That is a part of the original concentration. So the concentration starts at a certain level and is gradually decreasing. So the part is going to be whatever's left over after a certain amount of time. So the whole, we can choose whatever that whole is. Again, that's the initial concentration. We can choose it to be 1.0 molar. We could choose it to be 10 molar. We could choose it to be 3 molar. but 1.0 molar is a nice, easy number to work with. So, and the percentage is going to be 55% that's left over. So the part is what's left over after the reaction has gone on for a little bit. So in this case, we're told that 45.0% is complete, meaning that 45% of the reaction has, or of the reactant of the concentration is gone. So this is going to be 55% that's left. So 55% that's left is going to be equal to the part. The part is whatever's left over. That's going to be our concentration of A at time t, because the concentration of A at time t is whatever's left over at time t, because again, some of the concentration of A has been converted into product. So we're going to put that over the concentration, which is the whole, that's the initial concentration. So we're going to put that over the initial concentration, and then that's going to be multiplied by 100. Okay, so then this is going to be 55% equal to the concentration of A at time t over the initial concentration, which is 1.0 molar. Again, multiplied by 100, and then we can solve for the concentration of A at time t. So we can divide both sides by 100. So the 100 here cancels out there. It's 55 divided by 100 is 0.55. So we're going to say 0.55 is equal to the concentration of A at time t divided by 1.0 molar. And then, of course, we can multiply both sides by 1.0 molar. So this cancels out, and then we have 1.0 molar times 0.55 gives us the concentration of A at time t. Excuse me. So 1 times 0 times 0.55 is just 0.55. So the concentration of A at time t is equal to 0.55 molar, which is what we have up here. So this is a nice way to verify that this is correct. Okay, so now that I have my initial concentration and my concentration of A at time t, I can plug that in along with the time, because they give us time 65 seconds, so I can plug that into the equation. So I'm going to use this equation. So the natural log of the concentration at time t, which is 0.55 molar, so 0.55 molar divided by the initial concentration, which is 1.0 molar, so 1.0 molar. So the molarity is going to cancel out. That's going to be equal to negative K times T, which is 65 seconds. So now I can divide both sides by negative 65 seconds, because the negatives are going to cancel out there. This cancels out there. And so we're going to divide by negative 65 seconds here. And so when I calculate this, I get 9.19. So K is equal to 1.91. Oh, let me double check that again. 9.19, sorry, oops. 9.19 times 10 to the negative 3 seconds. And so that is the the K value. Oops, that should be per seconds, not seconds. Per seconds. So since seconds is on the bottom, we can say per second. So this per seconds. So just a review about the negative exponent. So if you have your unit on the bottom like this, 1 over s, 1 over seconds, you can rewrite that as a -1 because there's a 1 here. If you bring it to the top, then you change the sign and it becomes a -1. So same thing with x, like any variable, if you have x squared, 1 over x squared, that's going to be equal to x to the -2 value. So here, since we have seconds on the bottom, I can rewrite it as s to the -1 or per seconds. Okay, so here's our k value. Next thing is to find the half-life for this process. So now we need to use the half-life equation. Again, we have to make sure we're using the right half-life equation. Each order has a different equation, right? So first order has a certain equation, 0 order has a certain equation, second order has a different equation. So we need to make sure we use the right equation. So for first order, the half-life equation is equal to the natural log of 2 over k. Or if you do the natural log of 2, that would be equal to the 0.6, I want to say 693. 693 is correct. So 693 over k. And so since we calculated k, we just plug in k here and then divide. So then that's going to be equal to 0.693 divided by 9.19 times 10 to the -3 per seconds. And again, I have seconds to the -1 here. Let me make this clearer. So when I divide this, I can bring this up to the top and then again change the sign. So seconds to the -1 becomes seconds to the +1, which is just seconds. So if I divide these, I get, what do I get? I get 75 seconds. So this is equal to 75 seconds. So that is the half-life of this process. So here's the K value, here's the half-life. I hope this is helpful. If this was helpful, if you enjoyed this video and learned anything from it, then please by all means like the video, share the video, hit that like button somewhere over here. Also, do me a solid, subscribe to the channel, help me out here. When you do that, click that notification bell. When you click the notification bell, make sure you click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help solving, or if you have a topic you want me to cover, write that down below and I will do that for you. Thanks for joining me and have a great day.